Thanks for those who have stuck around to this point. Very excited to talk to you all today about WoFSCast and some of our latest developments with WoFSCast. The reason I'm giving this talk today and not Monte, Flora, who is the lead developer of WoFSCast, is because he's on break, as half the world seems to be right now. And so props to him, and he is creator of a lot of the content on today's slides. Okay, so for those who don't know, WoFSCast is a GraphCast-based emulator for the NSSL Warn-on Forecast System, or WoFS, which was actually recognized just yesterday with one of the OER Outstanding Scientific Paper Awards. WoFS and WoFSCast use 3-kilometer grid spacing, 18 forecast members, and focus on 0 to 6 hour forecast times. Predicted fields for the WoFSCast are UVW, temperature, geopotential height, and vapor mixing ratio at 17 levels. So every third level in the WoFS of the WoFS set of vertical levels, which is the same as the HER. And then also 2-meter temperature, composite reflectivity, and rainfall for a total of 105 state variables. WoFSCast is trained on 10-minute forecast data, which makes it pretty unique. So this allows WoFSCast to have pretty high fidelity to simulated storm evolution, as we'll see in this presentation. WoFSCast has been trained on 136 cases from springs 2019 through 2021. So really only a little over 100 cases actually used for training, but that has been sufficient to generate a pretty successful product. So the deterministic performance, as well as a complete description of WoFSCast, are provided in our recent GRL paper, linked there. But I'll be showing a lot of figures from that paper and some ensemble performance results as well. So here's an overview of the WoFSCast architecture, again, based on GraphCast. So some of this will be familiar to some of you, and we've heard a lot about GraphCast already today. One important difference is that WoFSCast is modified to be trained and then run over a limited area domain that varies from day to day, just as the WoFS domain does. So the WoFS currently runs over a 900-kilometer domain, which is repositioned daily over the area of greatest interest. So in the top row of the figure, you can see the basic strategy. We input the 3D weather state, again, those 105 state variables I listed, and then WoFSCast predicts the change in that state over the next 10 minutes. So it's predicting the residual, not the full state. So it predicts the residual, adds it to the initial state to get the new updated state, and then rolls that out over this however many time steps you want. And again, we're focused on lead times out to about 6 hours. So this uses the encoder processor decoder strategy of GraphCast. Graph neural networks are used in each of those 3 phases, and those are illustrated in the middle panels, showing the encoding step where physical state information is encoded into the latent space on a coarser mesh, multi-scale mesh, and then the residual is predicted in the latent space, using 32 message passing layers during the processor phase, and then the latent representation is decoded back to the physical space onto the 3-kilometer grid. And it's noteworthy, you can see the multi-mesh there in the bottom panels. And so this is a triangular mesh. This is not the icosahedral mesh that's used for the global GraphCast. So this was one of the major modifications that was required to get this to work. You'll note that the finest scales in the multi-scale mesh at that refinement level 5 are still 11 kilometers. So where a lot of the magic is happening, the grid spacing is, or the mesh spacing is relatively coarse, but nevertheless we get high fidelity even at pretty fine scales. And the total model is about 50 million parameters. So just an initial taste of how WoFSCast does. On the left, we have about a 2-hour loop of a squall line simulated with WoFSCast. And then on the right, we have WoFS. So WoFSCast is trained on WoFS forecast. So we are actually seeking to emulate the WoFS itself. So we don't expect to exceed the accuracy of the WoFS. And we chose this strategy because we suspected, and subsequent experiments have so far confirmed, that had we trained on the WoFS analyses, we actually would have gotten results that were worse relative to observations, just because storm scale analyses oftentimes have very large errors. Obviously, as you might suspect, this case is a bit cherry-picked. It's a strongly forced case, so WoFSCast does relatively well here. But generally speaking, we've been pretty impressed with how well WoFSCast has done. And so I mentioned that, you know, we don't expect to exceed the accuracy of the WoFS with WoFSCast. So one might wonder, well, why do it at all? Well, of course, it's because we can get the forecasts out a lot faster with WoFSCast. Right now, it takes about 1 minute on one GPU to generate 18 forecasts, and on with the WoFS, the traditional dynamical WoFS, this would take between 7 and 15 minutes, depending on how much convection is in the domain, using over 1,000 CPUs. So that's why we've done this. Now we're looking at reflectivity contours with rainfall therein, and then outside of that, we have 2-meter temperature shaded. And again, showing very high fidelity of WoFSCast to WoFS. Rainfall is a variable that the ERA5 global emulators struggle with, largely because of the large errors in the ERA5 in terms of precipitation. But of course, we don't suffer that limitation because we are training off of the WoFS. And the WoFS itself predicts real-world rainfall pretty accurately, so the WoFSCast does too. So looking at some objective metrics, these are storm object matching verification statistics generated using the Skinner et al. 2018 method. So we have the familiar POD, SR, frequency bias, and CSI. On the top panel, that is matches between WoFSCast storms and WoFS. So we'd like to see all of these metrics as close to 1 as possible. And they look pretty good. Again, confirming that the WoFSCast is doing what it was trained to do, which is to emulate the WoFS pretty closely. And then on the bottom, these are matches between both WoFSCast and WoFS to MRMS storms, so observed storms as represented in NSSL's multi-radar multi-sensor data set. And you can see that the dashed and solid curves are pretty much right on top of each other. So again, the WoFS and WoFSCast emulate the real world about equally skillfully. And then on the right, these are probability matched mean composites using a method that I introduced in 2019. Basically, you take all of your storm objects and you center, say, 90-kilometer wide patches on them, and then you compute probability matched means over all of those patches to get kind of a, kind of an idea of systematic differences in storm representation between, say, 2 different models. And so what we would like to see is that the left and middle columns to look as similar as possible, and then the difference plots on the right to be as close to 0 as possible. And again, we're seeing that storm structure is represented, WoFS storm structure is represented very well in the WoFSCast. Another way to say that is the WoFSCast is emulating the WRF model very closely, even down to these storm and substorm scales. And beating the dead horse further, we can look at vertical cross sections. So first, looking at the stationary image on the left, we have a plan view of composite reflectivity, and then the dashed line is where we've cut a vertical cross section across. And then on the bottom, we have vertical velocity plotted, and then perturbation theta V to indicate presence of cold pools beneath the storms. And then we have green contours showing the convergence and divergence associated with the updrafts. And then so looking, again, comparing the WoFS on the left and the WoFSCast on the right, and then you can look at the animation as well. We're seeing quite a bit of fidelity of the WoFSCast to the WoFS. The WoFSCast is not perfect. It suffers the same forecast smoothing that all other emulators do. that are trained with MSE loss. And this is because this is well understood. It's because of the double penalty effect, where small phase errors, especially in highly intermittent fields like reflectivity, are doubly penalized, and therefore smoother forecasts tend to be more rewarded by these L2 loss functions. And so we do see that with WoFSCast. Now you may have, it's not obvious looking at especially 2-hour animations. The smoothing is really not obvious at all. You do see it in spectra like these though. So that if the dashed curves are a bit below the solid curves, especially as you approach the 2 delta X Nyquist. And then if you look in the bottom panels, we'd like those ratios to be as close to 1 as possible. But they do decrease as you approach the Nyquist frequency and as you look at later lead times. So we do have smoothing in the WoFSCast. This does become more detrimental at longer lead times, as we'll see in a bit. But there are potential solutions to this, one of which I'll be showing a bit later. Okay, so now looking at WoFSCast ensembles, everything I've shown so far has been a deterministic forecast. So here we're looking at 15-kilometer neighborhood maximum ensemble probability of composite reflectivity exceeding a threshold, and then MRMS is contoured for reference. So these are both 18-member ensembles. So here the WoFSCast has simply been initialized from the WoF. So this is the simplest possible WoFSCast ensemble that could be configured, and it works pretty well out of the box. These are close to 6-hour simulations, and this is a pretty good case. We get pretty good similarities between the two all the way out, but it's not always that way. So these plots, these are spread error curves for composite reflectivity, where we regard MRMS as truth. So we have spread, which is ensemble standard deviation on the left, ensemble mean error in the middle, and the spread error ratio on the right. And ideally that would be close to unity. So comparing the black and red curves, we see that that out of the box WoFS ensemble does pretty well. I mean, it's the spread is a bit deficient as we would expect. The ensemble mean error is a little low, but that's probably partly due to the smoothing that we saw. It's again, we don't expect that the WoFSCast will actually be able to beat the WoFs. And then the spread error ratio, it's not a tremendous reduction in the spread error ratio comparing WoFs to WoFSCast. It's already pretty good. But if you look at the blue curves, these are new results with a WoFSCast trained using CRPS loss following the AIFS CRPS implementation described in Lang et al. 2024. So this is something I've recently implemented into WoFSCast, and we see that the spread error characteristics are now on par with the WoFs, which is very encouraging. So I'll get back to that in a bit. Some might be surprised that even without resorting to using CRPS loss or diffusion, that these deterministically trained WoFSCast ensembles can perform as well as they do. And one reason this is because the WoFSCast actually does emulate the butterfly effect, unlike many other emulators. This paper by Sells and Craig 2023 recently pointed out that the global deterministically trained emulators are incapable of learning the growth of low amplitude errors due to errors in the ERA5 reanalysis on which they're trained. The butterfly effect is simply not represented in the ERA5. It's simply dominated by unavoidable reanalysis errors. But since WoFSCast is not trained on analyses or reanalyses, but rather on the forecasts themselves, it does not suffer this limitation. So we actually get pretty reasonable spread growth, even without using diffusion or other methods. So you can see that on the right, these are vertical velocity spectra with tiny perturbations added at t equals 0, and then you see that rapidly grow up amplitude and upscale with time, which is the expected evolution. This is vastly different than what we see with the deterministic global emulators. So this probably explains why we get good ensemble spread growth with WoFSCast. And we attribute this to both the very small 10-minute time step that we're training on, and perhaps more importantly, the fact that we're using forecast data that are in a sense errorless. We can perfectly emulate, we can theoretically perfectly emulate storm evolution, at least as represented in the WRF model, because we're training directly on WRF forecasts. All right, so getting back to the CRPS loss trained WoFSCast, the way this is done is during training, each sample is used to generate mini ensembles. In this case, we follow the AIFS implementation and generate batches of 4 samples during training. And then we can actually input a forecast distribution to the CRPS loss function, since that's a probabilistic loss function. It requires an ensemble forecast. These training samples are stochastically perturbed using noise embeddings injected into the model. So that's partly described in the paper, but I had to dig into the Anemoy code to see exactly how that was done. And I'm pretty sure I've implemented that correctly with WoFSCast. The model learns to generate individual forecasts that can be combined into ensembles with near optimal spread. So basically, the model is learning how to take noise inputs and then basically use those to alter the individual to alter the individual forecast realization such that you get proper spread that's consistent with the ensemble mean errors. And then the forecasts are spatially sharper since the double penalty effect is largely mitigated. Since we're not using an MSC or MAE based loss, we're no longer rewarding overly smooth forecasts nearly as much. So again, back to this slide again showing the CRPS trained WoFSCast improving upon the vanilla WoFSCast in terms of composite reflectivity spread. And then we can look at other metrics like these are spread error plots now for storm centroid displacement errors. So basically displacements between the forecast and MRMS storm objects. And again, the blue and the black curves are pretty much on top of each other. And then now looking at ensemble fraction skill scores for 9-kilometer neighborhood maximum ensemble probabilities of composite reflectivity exceeding some high threshold. We see the dashed and the solid curves get much closer together with the CRPS trained WoFSCast versus the regular WoFSCast. So again, all of these metrics showing that with using CRPS loss, we're improving an already impressive WoFSCast. Okay, so switching gears a bit, this past May, we showcased WoFSCast, the regular version, not the CRPS trained version, in the hazardous weather testbed spring forecasting experiment here in Norman. And in a next day activity, we have participants score and provide their comments on how WoFSCast compared to WoFS, both deterministic and probabilistic forecasts. And so the 2 main takeaways: first, at 0 to 3 hours, participants thought the WoFS and WoFSCast deterministic and probabilistic forecasts were often nearly indistinguishable from each other, which was encouraging. And then at the longer range, 3 to 6 hours, the WoFSCast smoothing did become more evident. Again, hopefully this can be mitigated with the CRPS loss now. And then the smoothing often compensated the WoFS storm count and intensity biases. So the WoFS does run hot. There tend to be too many storms. They tend to be too intense. This is a classic example of model being right for the wrong reason. Basically, we have compensating errors between that WoFS hot bias and then the smoothing that occurs in the WoFSCast. So here's an example of one of the cases. This was actually showcased by one of the SFE facilitators. Um, they made the point that in this case, the WoFSCast actually did a better job in some sense than the WoFs. If you see the southern 70% contours, there's a little bit better correspondence with the MRMS, the magenta contours in the WoFSCast. I would say that's a coincidence. Again, there's no reason to expect the WoFSCast can systematically beat the WoFs. But the main point is that the WoFSCast did a pretty good job. And sorry, so on the bottom, those are ensemble forecasts, the neighborhood maximum ensemble probabilities that I've been referring to, and the top is just the first member of the WoFs and the WoFSCast. So comparing deterministic forecasts. And here is another case. Now we're looking all the way out to 5 hours. WoFs on the left, WoFSCast in the middle, and then MRMS on the right, which I don't know why I didn't label that, but so here is a case where the WoFSCast smoothing compensates the WoFS hot bias and actually ends up with a result that in some sense is actually closer to reality. So like if you look at hour 5, the WoFS is very hot compared to the MRMS observations. But the WoFSCast is notably smoother. And that's, if you compare forecast hours 1, 3, and 5, you see the WoFS is about as intense at all 3, but the WoFSCast overall gets lower amplitude, lower reflectivities. So it just fortuitously, it works out fortuitously in this case. Now, participants were asked to rate WoFS and WoFSCast on scales of 1 to 10 for 0 to 3 hours, 3 to 6 hours, and then deterministic and probabilistic. So the main takeaways are first that the WoFSCast scores pretty high. It's lower than the WoFS as expected, but not that much lower, although the gap does increase at the longer lead times. And again, this is expected given the increasing WoFSCast smoothing. Also, there were some interesting corner artifacts that manifested in some of these cases that we should be able to fix in time for the next SFE that may have worsened some of the WoFSCast scores. That's not something we had observed before. So it was an interesting thing to see. Okay, so future plans for WoFSCast. We have a growing catalog 1 kilometer WoFS cases, so we are definitely looking forward to training 1 kilometer WoFSCast. We are working on a grid invariant version of WoFSCast, which would ideally enable us to continue training on relatively small domains, but then at inference be able to run on arbitrarily large domains. Training on those much larger domains would be, pretty prohibitive. That's something Daniel was talking about this morning in the context of HERCast. It's just very difficult. I mean, GPU memory can only hold so much. We're interested in AI-powered data assimilation. One thing that holds us back from being able to take full advantage of AI is that massively large ensembles are not that useful if the entire ensemble is heavily biased. So if we can improve our initial conditions, we could then maybe get a lot of benefit from running forecast ensembles with more than 18 members. We could run potentially hundreds of members in real time on GPUs. Monte has explored diffusion as an alternative to CRPS loss using both NVIDIA's core diff and also the GenCast approaches. This work is still very preliminary. One downside to diffusion is that it is very costly at inference, but we have more work to do to see which of either of those would be preferable. We are interested in training a unit to diagnose additional fields from the existing WoFSCast fields. So just to see whether, if we want to add more fields to WoFSCast like CAPE and SEN, other things that forecasters would obviously want to see, do we have to add all of those to WoFSCast and therefore make WoFSCast ever bigger, or is it sufficient to train a much lighter weight unit to back those fields out? And then, in the future, if we want to add more fields, we just train additional units rather than having to retrain WoFSCast on potential years of data. We plan to have a real-time activity in next year's SFE. This year's activity was just the next day. So perhaps we could actually assess the potential impacts of the reduced latency of WoFSCast versus WoFS in that activity. And finally, at some point, we will definitely have to port WoFSCast to Anemoy so that we can better integrate with Eagle and be able to both benefit from and contribute to the ongoing AI developments, AI WP developments throughout the community. That may be a fairly heavy lift. I'm not sure when exactly that's going to happen, but it's definitely going to happen at some point. So that is definitely something to look forward to. I think that's it. Yep, that was my last slide. So thank you for your attention.
Awesome. That was great. Thank you very much, Corey, for that, and team. And I'll go ahead and post in chat. So again, congrats on the OAR Standing Scientific Paper Award, and I put that in chat if anybody else wants to check it out. I look forward to reading it as well. So yeah, with that, I think we have time for a couple questions if anybody has any. I didn't see any in the chat, but for hands, yeah. Hey, Daniel, over to you.
Corey, nice presentation.
Thanks.
I'm happy to hear of your new results with CRPS laws.
Mm-hmm.
So one question I have is, we are struggling with taking advantage of more ensemble members, like the performance saturates after 8 members. So I think even with the default WoFSCast, you are easily going up to 18 members. And have you done the same with the diffusion model, and it does well with 18 members, or what did you do to get many ensemble members improve performance?
So and are you speaking primarily in terms of accuracy or computational limitations?
Accuracy, it could take as long as it, yeah.
I don't think Monte. Okay, so with both the CRPS and diffusion approaches, we have not. Okay, for diffusion, I'm pretty sure Monte hasn't experimented with more than 18 members. With CRPS loss, I have experimented with, I think, 72 members. So basically, the 18 WoFS initial conditions, and then 4 realizations for each of those, just using different noise embeddings. And yeah, I really did not, trivial improvement, if any, going from 18 to 72 members in that way. I think the biases in the initial conditions are just trumping everything. Now, outside of the context of, outside of, okay, so using the vanilla WoFSCast without CRPS loss or diffusion, I have played around with different ways of getting to larger ensemble memberships. Mm-hmm. And for example, adding spatially coherent noise to the fields, and that did seem to produce some improvements. But actually, the best improvements I got was simply by taking the 18 initial conditions and just basically inflating, just taking that spread and inflating it. So keeping the 18 members, but just increasing the initial condition spread, which is something we could do in a dynamical context. And that actually made the most improvement. So I wonder if that's something we should just be doing with our traditional ensembles. But yeah, so far using AI, I have not found a way to leverage AI to actually be able to leverage much larger ensemble sets. And I think this problem may be especially acute for storm scale prediction, where our analysis errors are locally going to be quite severe. Like occasionally the analysis will be missing entire storms, or the storms will be, much too weak. And then that can impact the surrounding environmental fields as well.